Okay, so now I'm going to start with the chi-square goodness of fit test. This is a particular type of hypothesis test that is related to what we studied in chapter number 7. In chapter number 7, we dealt with point estimation. Okay, wherein based on a sample, we used to estimate population parameters. So for example, what used to be the case, we used to have a certain population. Okay, let's say there were vehicles arriving at a signal. Right? Let's say in an hour. And out of this population, this general population, you have a sample which is which consists of, let's say, 10 values. Okay, it consists of 10 values, 10 values of the number of vehicles that have arrived in 10 different hours. Okay, so 10 values of this sample will pertain to 10 different hours. Okay, and based on that, in some hour you had 20 vehicles, in some hour you had 25, you had 22, and based on this entire sample you were trying to estimate what is the average rate at which the vehicles are arriving at this signal. Okay, this is what we exactly did. We applied a method of moments estimate, we applied maximum likelihood estimate, and based on that we estimated lambda, that is the Poisson rate, or let's call it mu. Mu is more appropriate as we used it. Okay, mu, which is the Poisson rate. Right, and you found an estimator for it, which was summation xi divided by n, and based on this you calculated a value. Okay, as simple as that. That is how you used to do it. Now here we took an assumption initially. If you realized it, I assumed that the vehicles arriving at a signal in an hour has a Poisson distribution. This was my biggest assumption, that vehicles at the signal have a Poisson distribution. That is, they are arriving at a constant rate. But what if this assumption is incorrect? What if the rate at which the vehicle are arriving don't have a Poisson distribution, and you assume an incorrect distribution and you assume this rate mu? Then obviously if this assumption is incorrect, this implies that this estimate that you have found is also incorrect, right? So that is what we are going to do here essentially in the chi-square goodness of fit test. I am going to check the distribution, okay, after estimating after applying this point estimation. Once I've applied this point estimation and based on that I figured out the value of mu is this, assuming a particular distribution, whatever distribution this is. Okay, I have assumed a particular distribution. I am going to check my distributional assumption, whether the initial assumption that I had taken, that the vehicles arriving at the signal had a Poisson distribution or not. You can have different sorts of data, you can have different sorts of distributional assumptions that you initially took, and then you will be validating your distributional assumption using this test. So this is a test of validating distributional assumptions. Okay, that's your purpose here. So how do I check whether the initial assumption that I had taken, that the data pertains to a Poisson distribution, was correct or not once I have performed this estimation? Okay, so whether my sample conforms to the assumed distribution. This is the question. Okay, and this is what I'll address in this section. Okay, so let's get into it. Okay, so the next question is, how does a chi-square GOF test work? GOF means goodness of fit. So I'll take an example to explain you this, okay, because it's understood best that way. Okay, so in testing whether a die is fair, the suitable model is probability that x is equal to I is 1 by 6, where I goes from 1 to 6. Okay, this is a very simple model that they have taken. This is basically a discrete uniform distribution that our die usually follows, that there are 6 outcomes, 1 to 6, and if it is a fair die, all the outcomes have equal probabilities, that is 1 by 6, 1 by 6, so on and so forth. Okay, where x is the number thrown. Okay, and the hypothesis will be h naught is number thrown has a distribution specified in the model. Okay, so we'll check that a given die that is given to us, okay, is a fair die or not. That is the comparison we are making. Okay, so h naught is number thrown has a distribution specified in the model, that is the die is fair, because the model here suggests a fair distribution, a discrete uniform distribution. So this is the equivalent of assuming that the die is fair and x follows uniform 0 comma 6, sorry, discrete uniform, right? I have to make it like this, discrete uniform 0 comma 6 distribution. This is my null hypothesis. Okay, that is what I told you, that is what we check here. We check the distributional assumptions, right? So that is the distributional assumption we are checking, that whether the die is fair and whether x follows uniform 0 comma 6, and alternative is the number thrown does not have the distribution specified in the model, so this is a biased die. Okay, or you can say that x does not follow uniform 0 comma 6. Okay, so that is how it works, right? Now if the die is thrown 300 times, okay, the die is thrown 300 times, which has the following results. These are the results of throwing the die 300 times. 43 times you have got a 1, 56 times you have got a 2, 54 times you have got a 3, 47 times 4, 41 times 5, and 59 times 6. Okay, this is your observed data. This is your sample. You can call it the sample. And based on this, you have to validate whether the die has a uniform distribution or not. Okay, whether all of these outcomes have equal probability or not. So you toss the die 300 times, you rolled the die 300 times, and this is the data set you observed. There are 300, a total, if you will add, it is 300 throws, and these are the values. So 1 comes 43 times, 2 comes 56 times, 3 comes 54 times, so on and so forth. Carry out a chi-square test to determine whether the data comes from a fair die. So we have to check whether the data comes from a fair die, that is die is fair. That is my null hypothesis. Okay, so that is how it works. Now under this, how do you check? This is your observed data. First of all, let's write our observed data. So instead of calling it fi, I'll call it oi. Okay, that is the kind of language we use here, the notation. So 0, 1, 2, 3, 4, 5, and 6. These are the 6 values that it can take, and the observed data values are observed frequencies. OI stands for observed frequencies. 43, 56, 54, 47, 41, and 59. These are all the observed frequencies. Now I'll write the expected frequencies. Now this is expected frequencies under H naught. Okay, this is expected frequencies under H naught. Okay, so expected frequencies mean that if the die was fair, that is X followed a uniform distribution, what is the expected number of times you'll get 1? What is the expected number of times you'll get 2, 3, 4, 5, and 6? Okay, and if you see, expectedly you'll get all of these 1 by 6 times. So 1 will arise 1 by 6 of 300 times, right, which will be 50 times. 2 will arise 1 by 6 of 300 times, which will be 50 times. So all of these values will come 50 times. That is what you expect, right? These are the observed values. Obviously they are not same as what you expect because there is some randomness, okay? But your expected values will all be 50, obviously, because all of them have equal probabilities. So these are your observed and expected frequencies, right? So this should be clear. Now how do we proceed with this? The point is that if the distribution is chi-square, the distribution is in fact uniform. If the distribution is in fact uniform, then the observed frequencies and expected frequencies won't have much difference. The difference should be very low, and the difference which exists should be random. Okay, difference should be random. That is, the differences between OI and EI should be random. That is our assumption here. What does random mean? Random means normal. Okay, that is, the differences between EI and OI will be normal. A few differences will be very less. Random always means normal. Okay, there is no bias. It's totally unbiased, totally unskewed. Few differences will be very small. Few will be very large. And most will be at the average. That is what I mean by the normal distribution, right? There is no, it's symmetric completely. So this is what your graph looks like if you remember, right? So if there is random difference between EI and OI, then the distribution for EI and OI will be normal. Okay, that when will it happen? It will happen only when the die has a uniform distribution. That is, this EI is correct and this OI is actually in confirmation with the uniform distribution, and the only difference between these two are random. Okay, there is no systematic bias difference. There is only random difference, because if you throw a die randomly, it is possible that exactly 50 heads would 51 and 52 and 53 and 54s won't come. Exactly, these won't come. There would be some randomness. And why does that randomness exist? Because it's a sample. Okay, so there is some bias. So that difference between the two, EI and OI, should be random if the distributional assumptions are correct. Okay, and that should have a normal distribution. So we say OI minus EI has a normal distribution, right? But then we do not check using the normal distribution. How do I check this? I make my test statistic using OI minus EI whole square. If you remember, see, OI minus EI has a normal distribution. The square of OI minus EI divided by EI will have a chi-square distribution. Reason is simple. Square of a normal distribution adjusted for scale. Why have I divided it with EI? I have divided it with the EI to adjust for the scale. Okay, so I have taken it to basically a lower sort of scale. Okay, so OI minus EI whole square divided by EI, this is our test statistic, and we take a sum of it. Our actual test statistic finally, if you see test statistic under H naught, is equal to summing over OI minus EI whole square divided by EI. This is your test statistic, and this has a chi-square distribution with degrees of freedom. I'll talk about it. Let's call it nu. So nu degrees of freedom. This is my test statistic. Okay, and I want this test statistic to be as small as possible. This is a this is a one-tailed test. I want it to be as small as possible, because if the distributional assumptions are confirmed, then OI and EI should be close. Okay, if my expected distribution and my observed distribution are just the same, then the gap between the two should be less. So I want a gap which is as less as possible. Okay, and that is why I take such a approach. Okay, so I would want my chi-square test statistic to be smaller than a particular value. That is my critical value that I'll have. So I will plot this on a chi-square distribution and see whether it lies in the region of acceptance, that is the inconsistency with h naught, or it lies in the critical region. Okay, so that's my approach here. Now let's compute all of these oi minus ei whole square divided by ei. So how will I do it? For the first one, it would be 50 minus 43 whole square divided by 50. This is how you calculate. I'll do it on a calculator for you, and yeah, let's do it on a calculator. So yeah, here's my calculator. Yeah, all right, so let's look at it on a calculator, right? So it's 50 minus 43 by 50. Okay, so 50. So I'll tell you an easy technique to do it. Okay, let's save these values in particular values of the calculator. See, I told you in the beginning that saving will come in handy. So how will I do it? See, 50 I'll save to, let's say, A. Okay, this is my EI. Okay, and 43 I'll shift store to B. Okay, this is my OI. Okay, so once I have these values stored, I can actually compute it as, I'll say, A minus B whole square divided by divided by A. Okay, this is how I can calculate it. So I can directly get it, 49 by 50, 0.98. So let's write it here. But the advantage of doing it like this is now you don't need to write the formula again and again. You can just change the saved values. So EI remains 50. So A is still 50. B becomes 56 this time. So 56, shift store to B. Now you want the value, press the up button. You have directly the statistic, you press equal to. B is now revised at 56. So this will change 18 by 25, 0.72. Okay. Now I need to change the value of B again. 54 I'll change, shift store to B. Right. Now again 54 is stored in B. Okay. Now I just press the up button. I can press equal to get the value. This is 0.32. Again 47, shift store to B. This value is changed. You take this, press equal to 9 by 50, 0.18. Okay, 41 and 50. Okay, so I have to change 41 to B. Shift store to B. Okay, go up, press equal to 81 by 50. How much is that? 1.62. This is a big gap. Okay, and finally 59. I have to store. So 59, shift store to B. Okay, press up button, equal to, yeah, it's again same 1.62, gap is same. Sometimes there is a doubt in this particular thing. Why do we square? Why do we not just check for normal distribution? It's just to give more weightage to more extreme values. See, I had discussed the logic for squaring in variance, if you remember, in my prerequisite video. If you have not seen that, see that please. So I had discussed the logic for taking the variance as summation xi minus mu whole square divided by n. This is my variance, right? Why do I square here? Why don't I just take modulus of the differences? Okay, instead of taking in square. This is a logic that I've discussed earlier as well, and the logic for this is that I want to give a higher weightage to the higher gaps. Okay, more the difference, I want to amplify it more. For example, if the gap is of 2, if I square it, it becomes 4. Okay, but if the gap is of, let's say, 4, I square it, it becomes 16. So it gives more weightage whenever I square. So here I want to penalize more for higher gaps. Okay, since see, 41 and 50, the gap is very high of 9, so it became 1.62. 47 and 50, gap is only of 3, so it becomes 0.18. So see, the gap between 47 and 41 is not that much. Okay, if you see percentage wise, right. So here 3 and it just becomes 9. 3 and 9, the gap is not that much. But if you see in terms of this statistic, the gap is huge, 0.18 and 1.62 is so many times of that. Okay, so almost like 9 times of it, right? Exactly 9 times of it, in fact. So if you see, that is my purpose here. Squaring amplifies the gap. So I want to penalize more for higher gaps. Okay, if there is too much gap between EI and OI, I want to highlight that specifically, because that means there is no confirmation to my distributional assumption. EI and OI are being very different. So that's the logic for squaring. And obviously, as I've told you, the square of a normal distribution, if it is there, it has to have a chi-square distribution. So that's the logic. Okay. Now let's add this up. What is the sum of all of these? Okay, so add them up. 0.98 plus 0.72 plus 0.32 plus 0.18 plus 1.62 plus 1.62. Okay, this becomes 5.44. Okay, now I have to check whether this is too high or not, whether the square of the gap adjusted for scale between OI and EI is too high. If it is less enough, then it is fine. Then I would say, okay, this is less, and the distributional assumptions are confirmed. So I'll check at 5% level of significance. Okay, so I'll take the chi-square distribution and I'll check where does this value lie. Okay, so how do I do that? For that, I need the degrees of freedom. Okay, degrees of freedom in this case becomes n minus 1. So if you have got n groups, okay, you have got 6 groups here. Degrees of freedom becomes n minus 1, which is 5. Okay, n is equal to 6. I'll tell you more about degrees of freedom. I'll discuss eventually what are other adjustments to degrees of freedom. But in general, when your total number of groups here is 6, then your degrees of freedom just becomes 5. Okay, that is n minus 1. So I'll have to take chi-square 5 distribution here. Okay, so test statistic under H0 is 5.44, has a chi-square 5 distribution. Now you have to check what is the chi-square upper 5% percentage point. If you see this, okay, let's go down. Yeah, chi-square probabilities, I have to go for percentage points, right? So percentage points, if you see, upper 2.5% percentage point is what I have to see now. So it's right here. You have to go for chi-square 5. Okay, chi-square 5, you have to see, sorry, 5% percentage point of chi-square 5 distribution. It's 11.07. Okay, I'm checking at 5% level of significance. It is a one-tail test because I do not want a very high value. Low value would do. Low value means EI and OI are not very different. They are close enough, which is good, which means there's not much gap between each EI and OI. Okay, which means the distribution is a good fit. But if it is high, it means there is too much gap between EI and OI. Okay, so that means it is a one-tail test. One-tail test I have to see only at 5%. Okay, so 5%, 11.07 is the value. So your distribution, if you see, would look somewhat like this. Let it load. Okay, this is what you have. You have 11.07 here. Chi-square 5, right? Chi-square 5. 11.07. But my test statistic, it's 5.44. So it's in the acceptable region. Okay, so I say that test statistic under H0 lies in the region consistent with H0. Okay, so we don't have sufficient evidence to reject H0. Right, and we can say that the data confirms to a uniform 0,6 distribution, and the die seems unbiased. So this is how you conduct such a test. Okay, now we'll discuss a bit more about degrees of freedom soon, but this is our analysis for this question. Okay, I think it should be very clear to you. I've gone in a lot of detail for this one. Okay, Let's look at this other question. The table below shows the causes of death in elderly men derived from a study in the 1970s. So there was a study in 1970s. Carry out a chi-square test to determine whether the percentage can still be considered to provide an accurate description for deaths in 2000. So now they have not specified a particular distribution, rather they have stated a discrete distribution here with these probabilities. So these are your values for xi. Okay, it can be cancer, heart disease, other circulatory diseases, respiratory diseases, and other causes. Okay, and these are the probabilities, respective probabilities. So this is a complete probability distribution. If you add all of these, you will actually get 1. Okay, so this adds up to be 1, right? Total probability. Okay, now they have stated that we have to check whether this distribution is still applicable in the death cases in 2000. So in the year 2000, there were a total of, if you see from all of these cases, the number of deaths will be 286 plus 805 plus 1548 plus 755 and 464. This is the total number of deaths, that is 3858. So these 3858 deaths are divided in this proportion. Okay, and they are asking us whether this distribution conforms to the original distribution in 1970s or not. So this is your observed data, observed sample, right? And you have expected values as well. You have EIs as well. How will I calculate the expected values? Out of 3858, they are expected to be distributed with these probabilities if they follow the level of 1975, right? That is what we have to check. So expectation would be that our null hypothesis would be that the observation in 2010 or the death data in 2010 conforms to the to the 1970s level or 1970s distribution, right? And null hypothesis, alternative hypothesis will be the opposite of this, that the death data does not conform to the 1970s distribution, right? So this is the null, this is the alternative, very easy to understand, right? Now I'll take the expected values. So it will just be obtained by multiplying this 3858 with all of these probabilities. So the first expected value would be how many out of the 3858 deaths would be expected to be from the cancer? From cancer, it would be 8% of these. So 3858 into 0.08. Next one will be 3858 into 22%. So on and so forth. You can take all of these. Okay. So let's take these values, whatever those will be. Let's check. So I'll just put them in the calculator. 3858 is my mean value, and I'll just check 0.08 equal to, this is 308.64. The second one, these are my EI values. I'll just directly calculate all of these and write them for you. Okay. Once we have these, we need to calculate EI minus OI whole square divided by EI. These are our values that we need, and we'll sum them to get the test statistic under H0. Okay, so taking a difference, squaring, dividing by EI. Let's check. These are all the values that we have got. Okay, now let's add them up, right? So what is the total of all of these? EI minus OI whole square by EI, that will be my test statistic. Okay, let's check. Yeah, so this is the value of your test statistic. Now what is the distribution of this? It's chi-square. I have to take n minus 1 again here. No changes, it's same as the last time we did it. So there are 5 of these groups. 5 minus 1 will be 4. So the distribution is chi-square 4. And now I have to see the critical value. Have they no, they have not indicated the level of significance. We'll take it to be 5%. So this is my chi-square distribution. upper 5% percentage point is what I'll try to find. Chi-square 4. So chi-square 5%, 4, it's 9.488. 9.488. This is within the region of acceptance. So this is consistent with H naught. And thus we do not have sufficient evidence to reject H naught. That's how it works. So the 1970s data can still be applied in the year 2000. That's your conclusion, right? So that's how it works. Okay, let's move on to the next type of question. Okay, this is my final example where I'll show you what to do about degrees of freedom. There are a few adjustments related to chi-square degrees of freedom in chi-square goodness of fit test. So that is the particular thing I'm going to talk about, that what are these degrees of freedom that I have to take. So far we have just taken the number of groups we have -1. So we always used to take n-1 as the degrees of freedom. But there's a further adjustment. Okay. We'll see how it works, but first of all, let's take this example. So this example says the number of claims made last year by individual motor insurance policyholders were. So there were motor insurance policyholders which made given number of claims in a year. 2962 policyholders made 0 claims. They made no claim. 382 policyholders made 1 claim. 147 policyholders made 2 claims. 25 policyholder made 3 claims and 4 policyholder made 4 or more claims. Okay. Now carry out a chi-square test to determine whether the frequencies can be considered to confirm a Poisson distribution. So we have to check whether this forms a Poisson distribution or not. Okay. So this is a simple chi-square GOF test, goodness of fit test. We have to check whether the data conforms to our assumed distribution, that is the Poisson distribution, or not. So let's write this data first. So I have got the various values for X, which is the number of claims on a given policy. So 0, 1, 2, 3 and greater than equal to 4. Okay, these are the options, and I have got observed frequencies. I've already got. Expected I have to calculate. Observed is 2962, 382, 47, 25 and 4. Now if I go for calculating the expected frequencies, I'll have to calculate them using the Poisson distribution. Now if I use the Poisson distribution for the calculation of the expected frequencies, the challenge is to first of all estimate the lambda of Poisson distribution. Okay, that is the value lambda hat. What is the estimator that I'll use in order to evaluate these expected claims? These have to be based on the Poisson distribution. That should be clear to you. Okay, because they are expected. Expected means in line with the Poisson distribution. As per the Poisson distribution, what are the expected claims? As you saw in the first question, we calculated expected claims based on the uniform distribution. In the second case, we were given a discrete distribution. We used that to calculate the expected claims. Observed was always given, right? Now we'll see Poisson, but Poisson this time lambda is not given. So for lambda, we'll take the MLE of lambda. We'll take the MLE of lambda. What is MLE of lambda? It's X bar, if you remember. The estimation for the rate of the Poisson distribution, the MLE estimator, is the mean itself, the mean of the data, that is X bar. Okay, so I can calculate X bar. How do I calculate X bar? I will have to calculate X bar based on this data itself, OI itself, right? So let's do that. So my X bar will be, it would be a weighted average. These are the frequencies. Okay, these are observed frequencies, right? You can see them as frequencies as well. So frequency into X divided by the total number of frequencies. So 0 into 2962 plus 382 into 1, 1 into 382 plus 2 into 47 plus 3 into 25 plus 4 into 4. I'll consider these to be 4, not greater than equal to 4. I'll take them to be 4. I have no option here. Okay, divided by the total of these OIs. So the total number of policy holders that I had It's not written. I'll have to add them up. So let's add these numbers that I've got. What is this? So this is your result, sum of all of these, and I'll divide it by these. So 3420. So let's see what is the value of my x bar, or let's call it lambda hat. So what is the value of lambda hat? Okay, let's see. So this becomes 0.1658. Okay. So this is what you have got, right? So now based on this lambda value, I can actually find the probability of getting 0 claims on a policy, 1 claim, 2 claim, 3 claim, 4 or more claim. I can find these. How will I do that? Let's see. So probability x is equal to 0 will be e to the power of minus lambda, that is 0.1658, lambda to the power of 0, 0.1658 to the power of 0 upon 0 factorial, right? Probability x is equal to 1 will be equal to e to the power of minus 0.1658, 0.1658 to the power of 1 upon 1 factorial. So you can check this out for up to probability x is equal to 3. Okay, so let's find and even then I can find probability x is greater than equal to 4. So let's do these directly on a calculator. There's an easy way to do it on the calculator by saving the values. I'll show you how to do that. So let's open the calculator on this. Okay, this is my calculator. So now the best way to do this is that you write this equation by taking this value which is changing 0, 1, 2, 3, 4, it will change, right? This is the PDF of the Poisson distribution, right? That is what I've done here, right? To find the probabilities, I've used the Poisson distribution because x follows Poisson 0.1658, right? Okay, so these are the probabilities that I need to find. So how will I do that? So it would be, let's say, e to the power of minus lambda. So e to the power of minus 0.1658. Okay, this is not a value which is changing, into 0.1658 to the power of, let's call it a. Okay, a, this value is a, divided by a factorial. So shift and I can put factorial here. This is my value. I can press equal to. This is coming out to be 0. It's fine. I need to put 0 first of all in place of a. Okay, so press AC, shift 0, shift store to a. I put in a as 0, press equal to. This is your value. Okay, fine. Let's check what it is. It is 0.8472. Okay, yeah, 722. Cool. Let's make a as 1 now to find the second one. So 1, shift store to a. Whenever you have repetitive values, you have to find the same expression again and again. Use a variable and keep changing the values. Press up, you get it again. You press equal to. It's 0.14047. Okay. Next one, I have to make a as 2. So probability x is equal to 2 will be equal to, I have to make a as 2. So 2, shift store to a. These things, these small tricks will help you fasten your speed in the exam. Okay, this is 0.01164. 0.01164. Okay, this is clear. 3, I have to see for 3. So 3, shift store to a. Now press up, press equal to. This is 0. It's to the power of minus 4, right? So 0.0006435. Okay, yeah, I'll leave it at, I should leave it at 64. Yeah, so these are all my values. I've taken all of them to 5 digits, and greater than equal to 4 would be 1 minus all of these. So I'll take 1 minus all of these. So it would be 1 minus 0.84722 minus 0.14047 minus 0.11011164 64, right, minus 0.00064. Okay, whatever is left is your last one, so it is 0.00003. Okay, these are all your results. Now once you have these results, you can find EI. How will you find EI? See, as we did it in the last case, okay, this total of 3420 policies will be divided in these proportions. These are the proportions, right? These are the ratios. So you need to multiply them with this value of 3420 to find the to find each of these values, right? So let's just multiply and find out. Okay, so 3420 into 0.84722, right? It's 2897.49. 2897.49. Okay. Second one, 14047. 480.41. 480.41. Fine, cool. Two are done. Third one, 01164. 39.81. The next one, 0.00064. It will be 2.19. And let's see the last one. It will be 5 times 0 and 3. So it would be 0.102 or 0.10. Okay. These are your values for EI. Now your test statistic, if you remember, it is OI minus EI whole square divided by EI. Now if you'll see one important thing here. For these last groups, the last group, if you'll check here, your EI is very small. It is 0.10. Okay, even in the third one, x is equal to 3, your EI is small. It's 2.19. Okay, and when you'll take these values of EI and you'll divide this OI minus EI whole square with this value of EI, it will unnecessarily be inflated. If you divide this thing, the last one, last OI minus EI whole square divided by EI, if you calculate this will be 4 minus 0.1 whole square divided by 0.1. Just see the value of this will be huge. Okay, what will be the value of this? 4 minus 0.1 whole square divided by 0.1. This comes out to be 152.1, which is an absurd value here. Why is this absurd value? Why is this value absurd? Because the gap between them is, okay, it's just 4 policies that we are talking about. Okay, just 4 policies that have a claim higher than 4, that have more than 4 claims. Okay, and they will influence my test statistic by 152.1, which is absurd, which is very big. So it's absurd to take this value of EI, which will inflate my last category 10 times. Okay, which is unnecessary. So instead of doing this, what we do, we follow a rule. There is a rule. Okay, this is, I'll write a couple of rules here. Rule number 1. Rule number 1 is that whenever you have any group, okay, what is a group? These were my group number 1, 2, 3, 4 and 5. Okay, any random variable value or any group against which EI is less than 5. Whenever, this is a rule of thumb, remember it. Okay, whenever EI is less than 5, it will unnecessarily inflate your test statistic. Okay, it will just, it will increase it too much. So you merge this group. with the closest group or immediately preceding group. Let's say with the immediately preceding group, just the group which is previous to it. Okay, so what I'll do is in both of these groups the EI value is less than 5. The ones before these don't have this, but in both of these it is lesser than this. So for these two groups I'll add them to this group itself, the group which is 2. Okay, so I'll make my revised table. Okay, let's make my revised table. So I don't need to calculate this here. First, let's just calculate my revised table. This you'll only do in the previous two questions that we have dealt with. There were no groups where your EI was less than 5. I'll just show you. See, EI here, these are your EI values. See, they're very big. None of them are less than equal to 5. Okay. Even in the one before this, if you see, EI is all 50. None of them is less than equal to 5. Okay, so whenever they're less than 5, particularly, then you have to merge the groups. Now, how will I merge? Okay, let's make the new table with the merged groups. X values will be 0, 1, and everything greater than 2 will be combined with 2. So greater than equal to 2. I'll merge it here. Okay, obviously OIs also need to be merged. So 2962 is here, 382 is here, and you completely merge these three. Okay, because under them EI is always see EI, not OI, because EI only inflates the value of the test statistic unnecessarily. Okay, inflates mean increases. Right. So this is your OI value 76 here. Now EI I need to add these three, obviously the last three one. So EI you write the correct first two values. It's 2897.49. Okay, and then you have got 481.41. Cool, fine. And this last one, if you have you see, you have to add these three. Okay, 39.81 plus 2.19 plus 0.1. Okay, so your value comes out to be 42.1. Cool. 42.1 is your last test statistic. Now this is your revised table. Okay, and you just have to forget about your old table. It doesn't matter what the old table was, you have to stick to the new table now. Okay, so this rule is something you have to remember. Okay, now I have to calculate my test statistic, then I'll show you one more rule that I need here. Okay, EI minus OI whole square divided by EI. This is my test statistic. Let's compute it based on these values. If you'll take the sum of these three, you will find the test statistic as 49.26. This is your test statistic under H naught. Now you need to define your hypothesis. Obviously, H naught is that the data conforms to Poisson distribution. Data conforms to Poisson distribution. So that this data that we had gotten is from the Poisson distribution, and H1 is that data doesn't conform to Poisson distribution. Okay, these are your hypotheses. Okay, so under H naught, this is your test statistic. Now you need to see what is its distribution. It has to be chi-square. Now if you see here clearly, the distribution, there are three groups left, so it should be chi-square 2 ideally. Okay, you do not concern with this data anymore. No, this doesn't matter, only the new one does. So chi-square 3 minus 1, it should be 2. But there is one more rule that is applicable and that I haven't told you so far. So this one was the first rule that you had to see. Okay, this is my rule number 1. I'll put the rules inside the box, and yeah, I'll write them in a different color. Okay, right, so you have got, this was rule number 1. Okay, These rules I'm putting them in a box, right? Now you have to see what is the second rule. The second rule is whenever the data or whenever the observed data is used to estimate a parameter value, one degree of freedom is lost. Okay. See, degrees of freedom, you can think about them as empty spaces that you have which you can adjust. Okay. So whenever you have n spaces in general, okay, whenever you have n spaces, as soon as you fill up n minus 1, as soon as you fill up n minus 1, the last space is automatically filled. Okay, so whenever you have n groups, your degree of freedom is always n minus 1, simply speaking. Okay, that's the general rule. But there is a catch here. Whenever the observed data is used to estimate a parameter value, like we use the observed data here, if you see, we had done one special thing here. We had used the observed data to calculate this value of lambda hat. Okay, we had taken an MLE estimation for lambda hat, if you remember, right? Using the observed data, using this data that we had originally. Based on this, I had said, okay, my MLE for lambda hat is x bar, and x bar I had calculated using nothing but the observed data. Okay, so whenever you use the existing observed data to calculate the parameter value that you are taking, okay, then 1 degree of freedom is lost. I'll discuss the logic behind this very soon, but right now you just need to know the rule. Okay, I'll talk about the logic in a bit of detail, but here the point is that whenever you're using your observed data itself to estimate the parameter value, okay, here lambda was one parameter that we estimated through the observed data. This formula we have applied is using the observed data. So whenever you use the observed data to estimate the parameter value, then 1 degree of freedom you have to lose. Okay, if there were two parameters which were estimated using the observed data, then we would have lost 2 degrees of freedom. Okay, three parameters, 3 degrees of freedom. So for every parameter that you estimate through observed data, okay, 1 degree of freedom is lost, right? So that is one clear thing that you have to remember. So now in this case, let's just first apply these rules and then we'll discuss the logic behind them. Okay, so in this case, if you see, I'm left with three groups. Okay, generally in three groups my degree of freedom would be n minus 1, which is 2. Okay, but here in this case one more degree of freedom would be lost because I have estimated the parameter lambda through the observed data. So my degree of freedom would be 3 minus 1, because minus 1 usually comes in, and minus 1 more. It would just be 1. So I've got 1 degree of freedom. Okay. So this 49.26 has a test statistic under H naught has a chi-square 1 distribution, and now I have to check it as under the chi-square 1 distribution percentage point, upper 5% percentage point. So if you'll see, let's go to the tables first and let's be done with this question and then I'll discuss the logic. 5% chi-square 1, the value is 3.841. Okay, this is the value. If you see, my value for the test statistic is much larger. It is 49.26, much larger than the than this value. So I can say test statistic lies in the critical region. which means test statistic lies in the critical region, which means we can reject H naught at 5% level of significance, right? So the data doesn't conform to the Poisson distribution. That's our conclusion. Okay, right? So now I'll discuss these two rules again that I have given you. So these are important. These you have to always remember. Let's get into them. Okay, so I've already discussed the logic for the first rule. Any group against which EI is less than 5 will be merged with the preceding group. The reason is that when EI is less than 5, it inflates the test statistic, right? So we merge it with the previous group in order to increase the value of EI, and so that EI is not too less. Okay, unnecessarily it should not inflate the test statistic. Second is, whenever the observed data is used to estimate the parameter value, 1 degree of freedom is lost. Now what is the logic behind this? For this we need to understand a couple of things. See, first thing, let's start with the concept of chi-square GOF test. So chi-square GOF test, the purpose is to check the conformation of a data to a particular distribution. Now for checking the conformation to a distribution, you would need to know its parameter. Okay, whatever the parameter is, you need to calculate it. Now this parameter can be calculated two ways. Either it can be calculated based on a different data set. Okay, so maybe you have like let's say you had calculated it in the past. Okay, so you calculated it based on 1970s data. Okay, because you're checking the confirmation to 1970s data for the 2000 data. So you are basically calculating the parameter. In that case, we had calculated the entire distribution based on a different data set. Or you can calculate the parameter based on the observed data set. These are the two options that you have got. Right, different can be any different data set, and we can use that to calculate the parameter of the distribution that we are checking the validity of this observed data. Whether this observed data confirms to this distribution or not. That is what we are checking, and its parameter which you need can be calculated, its value can be calculated based on an entirely different data set or this observed data set. When you calculate it based on this observed data set itself, okay, you are using this observed data set to calculate the parameter, it becomes a bit unreliable, okay, because you are using the same distribution to calculate the parameter first, and then you are checking the confirmation of the same data set, right? So basically it's very absurd. It's absurd. Why? Because you're checking this observed data set and you're using this data set to calculate the parameter, right? So your parameter ideally should come from a different data set, should not come from the observed data set. But if you compute your parameter value from the observed data set, then basically you are reducing the reliability of your test. Okay, so you need to make the test more strict. You need to make the test more strict if you are using the observed data set to compute the value of the parameter, right? Because it is a very lenient test. It is a useless test if you're using, not useless completely, but it's not good enough if you're using the observed data set to compute the value of the parameter. So to improve the efficiency of this test, you need to make it more strict. And how do I make this test more strict? That is the question. So I do that by reducing 1 degree of freedom. When you reduce 1 degree of freedom, you make the test additionally strict. Why? Because you are using the same observed data to compute the parameter, which ideally you should not. You should use a different data set. Otherwise, there's no meaning of test. You're checking the observed data set, whether it conforms to the distribution, and you are using the same observed data set to compute your parameter, which is weird. So you make the test, even if you use the observed data, and especially when you use the observed data, you need to make the test more strict So you reduce 1 degree of freedom. Now, how does reducing a degree of freedom make the test more strict? Think about it. Okay. Here I was earlier supposed to take chi-square 2 distribution, but I took a chi-square 1 distribution, right? So if you compare the value of the two, if you see in this table, as the degrees of freedom increases, the chi-square value also increases. 1 degree of freedom, the value is 3.841. 2 degrees of freedom, the value is 5.911. 3 degrees of freedom, the value is 7.815, right? So it increases. Now if you see, earlier the test would have accepted any test statistic value below 5.99991. If the value was below 5.991, then I would have said, okay, this lies in my region which is consistent with H naught. Okay, any test statistic which is less than 5.991 lies in the region of acceptance, right? This is a more lenient test, but when I reduced my test statistic to 3.841, I reduced it further. Why did I reduce it? Because I want to make my test more stringent or strict. Okay, so then even if I have a test statistic which is less than 5.911, but you know, it is more than 3.841, still I'll reject H naught. Okay, still I'll say that the data does not conform to the given distribution. So reducing a degree of freedom reduces the acceptable test statistic value to confirm the distribution, to confirm with H naught. So that is how we make the test more strict. Okay, and reducing a degree of freedom, because we are using the observed data to estimate a parameter, is just a way to make the test more strict. So you should understand these things, why we are doing what we are doing. Okay, it's just an approximate method to make the test more strict, right? So this is all for this video. Now you can do more questions on chi-square goodness of fit test. There are a few given in the material, and if you face a difficulty, let's talk about those. So you can message me. But remember these two groups. Whenever there is a group with EI less than 5, you have to merge that group, okay, with other group preceding it. And also, whenever the observed data is used to estimate a parameter, 1 degree of freedom is lost. Observed data is used to estimate 2 parameters, 2 degree of freedom will be lost. So on and so forth. This is just a way to make the test more strict. Okay.